Okay, so today we are going to tackle the Quill Gold NFT CTF. I dropped a link to that in the chat, but it's also being shared on my screen. So let's just like quickly scroll through this and then we'll switch over to the code. So general goal of this CTF is to retrieve the password from the iPass manager and mint at least 10 NFTs. So we got to get 10 of them, not just one of them. They provide us some contract code and some Foundry setup. And they do note that this challenge involves interacting with a on-chain contract that's been deployed to the Goerli testnet. And so therefore they're going to fork that chain. So I'll also just like briefly talk about how they do that. They use a VM method via Foundry. So there's a little bit of configuration that needs to happen to support that. But that's generally the hack. So if we switch back over to the code now, I've taken this code already and dropped it into my VS code. Let's see. All right. So let's see. This is the test code that they set us up with, right? So we'll just start here to get a general sense of what they're looking for. They created a named hack actually already. So I just copied the naming that they use within their test function. They do a little bit of setup. What's happening here with vm.create_select_fork, this is just something that Foundry exposes so that you don't need to do it in the command line. Can you guys hear me? I know somebody had issues with this last time. Okay, cool. Yeah, maybe just check your audio settings. Yeah, so what this is doing is it's basically saying pull a fork based off of the Goerli RPC endpoint, and then this is the block number. So basically what they're doing is because they're deploying this contract to Goerli, they want to make sure that in case anybody interacts with it on chain, that doesn't mess up kind of the CTF. So they're just pinning it to say interact with the chain starting at this block number in the state that was saved at that block number. How do you like set that up? Like if you were to just try and run this, it would break on you. So in your Foundry like config file, you just create RPC endpoints and then add a RPC for the test net here. And then when you run the test, it will pull this RPC to fork the chain and deploy it locally for your test. So pretty simple and a nice little handy way to do that within your tests instead of doing it from the command line. But yeah, not a whole lot of info here. It's basically just deploying that, setting up the contract, and then tells you to implement your solution. So let's take a look at the actual code. It's very simple. So we have a storage variable for last token ID, a Boolean for minted. Then to take one NFT, so one, this gives us a clue that we'll probably have to exploit this somehow so that we can take more than one, but let's take a look at it. We pass in a bytes32 password, which is passed into this require statement. And this is calling a interface called iPass manager at this contract address. It's calling the read method and inputting our password. So taking a look, they have this interface up here. They only provide the interface for the read method. So, and we don't have that contract anywhere. So we're going to have to look up what's happening at this address on the testnet. And this is kind of what they're talking about as far as a real world interaction. So let's see. Yeah, that's a great solution. We'll just change the name. That should work. Cool. So we'll take a look at what's going on with this contract on chain, but then let's see the last part of this. We want to actually mint, right? So this is saying if not minted. So last token ID is going to increment. Last token ID is going to default to 0. The first time we call this, it'll increment. So the token ID is going to be 1. Then we safe mint. We want to send, of course, to the message.sender, which is going to be the attack contract that will implement, and then the token ID. And then minted equals true. So this is trying to prevent us from calling this multiple times. And if minted is set to true, we would get a revert here, so we aren't able to call back into this. We will come back to this, but some pretty straightforward issues with this, right? So, what we can just do is add an audit tag and say this violates the checks, effects, interactions pattern. Why? Because we have a check, right? The check is within the if statement, essentially, and there's a revert here. And then the effect is after the interaction. So what this should have been, right, to ensure that this doesn't have any reentrancy risk, you would want minted equals true to be here, not here. Like this would be appropriate CEI, but the way that they have it written is not, right? But we'll come back to that. Let's take a look at what is happening with the iPass manager at this address. So I'm going to copy this address, and we're going to flip back over to the to my browser so that we can jump onto Etherscan, and we're going to take a look on Etherscan what's going on with this contract. All right, Etherscan. I think everybody can see this, hopefully. Ah, cool. And we want to hop to the testnet. Give it a sec to reload. All right. Okay, so let's see what this contract looks like. Okay, so we just have a bunch of bytecode. It's not super helpful. We know that this is being casted to the iPass manager, and there should be a function called read on it, but this doesn't help us at all. Etherscan has this decompile bytecode functionality, so you can go and click decompile bytecode. Sometimes it takes a second. There are a couple other tools that you can use this with. The DAW contract library is a great one if people aren't familiar with it. But while this is decompiling, okay, cool, here we go. All right, so the first thing it spits out for us is read. I'll increase the size of this in case it's hard to see. So this is the function we're looking for. The rest of it, all good, but really what we're looking at is read, right? So read currency, they're calling it currency. Who knows if that's right or not, but there's a bytes32 variable currency. In our context, that's password. It does some checks on the value, like, and remember, we're working with a decompiler. So because we're working with a decompiler, like, take some of this for what it is. But most important thing here is what this is returning. And it's returning a Boolean, and it's looking at the storage slot defined by currency, aka password. So this means that there's a certain storage slot that we can pass, which probably has a value of true at that storage slot. And then that would allow us to pass the password check. What we know from the contract still is relatively minimal, but we just know that at some point they must have stored a true value with the password. It looks like, maybe they could have used it with this define set, right, where they're passing a bytes32 and a Boolean. The bytes 32 is probably the storage slot, and the Boolean, of course, is going to be true or false. And down here we see at the storage slot of parameter 1, they are setting it equal to the Boolean parameter 2. So at some point, they probably set a certain storage slot to give us the value of true. Let's take a look at the contract itself again. Looking at the transactions, there's a couple of read transactions that occurred, but primarily what we're interested in is contract creation. Let's see, did they do anything in the constructor to set a value to true? Taking a look at this, so this is really great. If you haven't discovered this yet, the state tab in Etherscan, it'll tell you how state is changing within that call. So it tells us, okay, like there's some value changing hands between the miner, and we know that this is the deployer if you look back at the Etherscan, but this is where some state actually changes. If we open this up, we see that this storage address, before this, there was nothing because there wasn't a contract yet. And then after, there's a value of 1, which we know in Boolean is true. So this storage address, we're going to copy that because this storage address has a value of true. So we can pass this to the password, and we should be able to get past this first require statement. So let's go back to our code and take a look at what this means. So I keep closing this. We'll pass in this value. So we know password equals this value, which we just grabbed from the Etherscan state change. And then this will pass. And then we just need to sort out how do we re-enter into this function so that we can mint more than 1 before this minted is turned to true. I'll pause real quick. Any questions in the chat? No? Okay, cool. All right, so let's just start building out the hack a little bit. So we're going to say, let's say, function exploit. Remember, no worries at all. So always like to have target. Let's see, and Copilot's trying to help me out, but we're going to just write it all out. So this is just like our target contract, right? So this would be the GoldNFT contract. And what we're going to do is we're going to say gold NFT of, we're going to cast the target address to be of that type. And then now Copilot's helping me out. Take one NFT is the function that we want to call, right? And we need to return this password value. And Copilot's reading that there. And so it's trying to pass it in for me right away. So we'll pass in that value. And then we need to take a look at the reentrancy. So let's see, we'll take a look at SafeMint. For anybody who went through the Securium course with me earlier this year or has done the Securium content on your own, you probably know where we're going with this. This is a known issue with the ERC 721 implementation, is that SafeMint, despite its name, not super safe and is vulnerable to reentrancy. Why? The mint function, nothing wrong with that. Mint's okay. And right now we're in standard ERC 721 contract definition. This is not something that the CTF engineered. It's not a change to the standard. This is the normal standard. So anytime you're seeing ERC 721 in the wild, you have to be aware of the fact that the SafeMint function has a reentrancy concern with it, and that is with check on ERC 721 received. So let's take a look at this function and what's happening here. So the concept of this function is that if a smart contract is minting or receiving an NFT, it wants to check that that smart contract address has implemented functionality to receive the NFT so that the NFT doesn't get locked in a smart contract that doesn't have a way to interact with that NFT. And so it checks to.code.length. So this would be address.code.length is greater than 0. This, in most cases, will tell you if a smart contract exists at this location or not. It's possible to violate this if you call an address within the constructor, but that's a different, that doesn't pertain to this. But if a contract already has been deployed, then this will return true because the code at that address is greater than 0. And then what it does is it casts the to address to a ERC 721 receiver contract type and calls a on ERC 721 received function. And what it expects is that this function on the contract that is receiving the NFT should return the function selector defined by this interface. That's all good, right? No problem there. But the vulnerability is the fact that this is now an external call to our smart contract. And in addition to returning this function selector, we can insert additional logic, right? So let's come here and let's say function, let me grab the name of this, I'll just copy it. And we're going to say on ERC 721 received. And then, okay, let's see how well Copilot does. Address, uint 256 bytes, call data. This should be bytes memory. External pure return, it's not going to be pure necessarily, right? Returns bytes 4, okay. Now, this is not exactly what we're looking for. It's not ERC721.on, it's this, right? So this contract dot on ERC721, because, right, received dot selector. And this selector matches the selector. Remember in Solidity, you don't have to pass variables here if you don't want to, if you're not going to use them, right? But we want the function selector to be the same as the expected function selector. So then here, what we can do is we can say GoldNFT. We can't pass the address of the target contract manually, but we do know that our contract in this case is being called by the contract we're trying to exploit. So Copilot's way ahead of me. We can just use message.sender. And then we're going to call the same function that we kick off here in our initial exploit function. We're just going to call it again. Why did it not complete the line? And so now what would happen is we would call this. We would enter into the smart contract. We would pass this. It would get to here. And then it will call safement before this variable is changed. And then in this call, when it eventually calls the check receiver function, we will then re-enter and call mint again, right? So now we want to just add some logic so that we can loop through this. And that is relatively easy to do. What we'll do is we'll create a state variable. And I guess we'll just make it, we're going to loop through this, right? So essentially, every time we enter this function, we're going to increment the value of I. And then we'll say, let's say we need to mint 10 of them, right? So for I is less than or equal to 10, call the function again to re-enter. Once we've minted those 10, we won't re-enter, and we'll just return the function selector as it's expecting, and we should be good to go. What doesn't it like here? I'm not seeing an issue. Maybe it's just throwing a linting issue when there isn't one. Okay, so at this point, we have most of our logic. We have the password. We'll re-enter a bunch of times. This smart contract that we're using to hack will receive all the NFTs. If we look at the attack, what is it looking for? It's looking for the hacker address to have the balance, not our hack contract. So the last thing we need to do is we just need to transfer these NFTs to the hacker. And so what we'll do is we need to iterate through it because we have 10 of them. So we'll say uint 256 token equals 1, and then token less than or equal to 10, and then token plus plus. What is this? This is the token ID, right? So we'll have GoldNFT. It's kind of getting there for me, but it's not exactly right. Dot transfer from requires who's sending it. That's us, this contract. Who it's going to, message.sender, because exploit is going to be called by our hacker. Oh, thank you. You're correct. This should be if, not for. Thank you very much. And then lastly, we need the token ID because it's NFT, right? So we're going to tell it the token ID that we are sending to ourselves. And we talked about the token ID earlier, but when it's minting, this is the token ID of the mint. It's initialized at 0. The first token that gets minted, it increments immediately before minting it. So the token ID is going to start at 1 and increment from there. So quick synopsis of this whole thing, right? So we use Etherscan and the decompiler to find out that this is the password that is being set when the contract is deployed. So we're going to use that password to get past the first check in the CFT. And then the known vulnerability in ERC 721 implementation that this on receiver check for smart contracts has a reentrancy vulnerability. And they did not use the check effects interactions pattern. If they had, they would have been protected, but they did not. So we can exploit that reentrancy. And then lastly, we transfer all the tokens back to the hacker. So now looking at the attack, this is pretty simple. We're just going to say hack equals new hack gold NFT, right? Hack is defined up here. We're importing the contract up there. And then we just simply say hack.exploit. And our exploit, we need to pass the contract that we're trying to attack, which is NFT, which again, they defined up here. And then that should all work. So if we come down, I'll clear this out. And we say forge test, I'll add a bunch of V's to it so we can see the call logs. It's going to compile this up for us. Cool. And it was successful. So here you can see all the transfers that are occurring. And this is hard to read because of the width of my terminal. But you can see how the reentrancy works if you flow through this. And you can see how it wraps and unwraps itself within the reentrancy, right? So as we reenter, we go deeper and deeper, right? And then this is the 10th call in, and then you see we're returning the function signature over and over again, as that's what's expected as we come out of the reentrancy. And then all of these are owned by our hack contract, and it sends those to us. Now, let's just to really prove the point, right? So let's modify this contract form and put that there and see what happens, right? If we run our test. Right? Fail already minted, which if they had followed checks, effects, interactions, the second time that we attempt to mint an NFT, it would fail on us. So that's why you should always follow checks, effects, interactions. Even when you're using reentrancy guards, follow checks, effects, interactions. Even when you're using a smart contract language that tells you that there are reentrancy guards in the compiler, still use check, effects, interactions. Further, it never hurts to use guards on your code so that you check invariants every time a function call happens to make sure that the invariants of your contract are still true and unexpected things aren't happening. Use all those standards and you won't run into these types of issues. But I think one of the coolest things from this, like we see a lot of reentrancy stuff in CTFs, but using the decompiler, knowing that Etherscan will tell you what storage values change on every single transaction. If you just click on that storage tab, those are kind of like some cool takeaways from this. Any questions? I mean, that's the hack. A lot shorter than last week, a little bit more straightforward, but nice to kind of whip through one of these. Okay, so let's see. Looked at the NFT contract, found which checks it does, looked up those checks worked, bypassed them. Yeah, essentially, right? So like the general flow when you're doing this type of thing, like this is a great one because the code itself is simple and we're not doing a bunch of code skimming to try and find the vulnerability, right? If you're doing an actual audit, you got to spend a lot of time getting comfortable with the code. With CTFs, you know there's an exploit, so it's a little bit easier. What I always generally do is you check the compiler version, check what's being imported, look at your state variables, and all CTFs, the structure is generally that there are require statements that you need to pass, and you need to know like the tricks of vulnerabilities or like the ins and outs of the EVM or something like that in order to pass the require statement. And so that's why we like went through the compiler and we're like, okay, we obviously have to look on chain to see what happened here. This is a little bit of knowing like that there's a vulnerability in the safe mint function. But if we didn't know that, right, we would just say, okay, this doesn't follow checks, effects, interactions. We need to re-enter here. This is the only function call. Let's follow this. Safe mint, you go to safe mint again. So you have safe mint down here as well, right? So mint, you would dive into mint. You would look at that. Is there anywhere within mint that makes an external call? No. So then you would check the next function, which was the on receiver check, right? So look at Solidit. You'll see a lot of this stuff pop up. With CTFs and of course with audits or anytime that you're developing smart contract code, you have to be really careful about making calls to external contracts, no matter what that looks like. Because when you make a call to an external contract, you are introducing the opportunity for somebody to insert logic into the flow of that transaction call. So that's kind of how you want to step through these things. And if you're doing an audit and you see external calls, make sure that that external call is really well locked down and that there are the necessary checks in place to ensure that that external call isn't injecting unexpected logic that could change the control flow of the smart contract. Cool. Any other questions? For anybody who's joining late, this is going to go up on YouTube pretty quick. So should be easy to run back through it if you didn't get to see it all. Cool. All right, guys. Thanks a lot for joining. Have a great Friday, and I will see you next week. Talk to you later.